Hey chemistry peeps, Jess McCartney here. So today we're going to start talking about some green chemistry principles, and where I want to start is treated pine. So we use treated pine for lots of different sources, fence palings, for different carpentry, building materials, but treated pine can be done in two different ways, and these two different ways it depends on whether the company wants to adhere to green chemistry principles. So one of the ways is using a copper arsenic derivative, which can be quite toxic to the environment. And the other way is using an alkaline copper material. So both of these ways can treat the pine, but one adheres to green chemistry principles and the other doesn't. So we're going to talk about them further in the lesson. So we are talking about fuel cell challenges and innovations today. The study design dot points that we're going to cover is contemporary responses to the challenges and role of innovation in the design of fuel cells. And we're going to talk about this in reference to green chemistry principles and design for energy efficient and use of renewable feedstocks. So in 1998, a set of 12 internationally recognised principles of green chemistry were devised. And the main reasons for these green chemistry principles is to reduce the impact of chemical processes on the environment, to reduce the waste on Earth, to reduce polluted water supplies, reduce atmosphere being filled up with harmful gases, and reduce the energy being wasted in inefficient processes. So these principles should be reducing all of those things, and chemists and scientists have to devise different ways on chemical processes if these principles weren't being adhered to. So what do they focus on? They focus on designing processes to minimize raw materials required and waste produced. So what that means is that they want to be able to use as many raw materials as possible and reduce the amount of waste or byproducts that's being produced at the end that are just going in landfill or are just going into the atmosphere. Using renewable, safe and environmentally friendly, harmless materials where possible. So this could be examples of using water as a solvent instead of a harmful solvent such as benzene. And maximize energy efficiency of reactions. So trying to find the quickest way possible for the reaction, but without producing those harmful side products. So what are the 12 principles of green chemistry? So they are prevent waste. So that's trying to reduce the amount of waste possible. So this is either as the reactants or as byproducts. Design safer chemicals. So what that means is that the chemicals that are being produced, they want them to be safe for consumers and for the environment. Find safer ways to make synthetic products. So this could be using different reactants to make safer products, to think about the byproducts that are being produced or the products themselves to make sure that they don't degrade and form toxic products as they degrade. Maximize atom economy, so using as much of the atoms as possible without those side products. Use safer solvents. So this is like water instead of benzene. So using the safer solvents to dissolve reactants as possible. Use renewable reactants. So instead of using the fossil fuels, trying to use those materials that are renewable and that can be renewed over a short period of time. Maximize energy efficiency. So this could be using energy that's being produced in the reaction or using the energy or the least amount of energy in the reaction as possible. Avoid chemical derivatives. So this is like tinkering with the chemicals too much. So try to use the chemicals or the raw products as is. Use a catalyst where possible. Catalysts are useful for speeding up the rate of reaction, which is listing in one of the other principles. So we want to be able to use catalysts to increase that energy efficiency and to increase that reaction rate. Use biodegradable products. We don't want products sitting in the environment for long periods of time, and this is where the plastics and things that we're trying to deal with now that just don't degrade. So we want to be able to produce those biodegradable products that degrade over a short period of time that are not toxic to the environment. Use real-time analysis to prevent pollution. So what this means is that scientists need to be able to analyze the reaction that's being done and be able to collect any byproduct pollutants that are being produced as they're being produced. So this would stop them going into the environment as a side product. and minimize the potential for accidents. So this is running your risk assessments, understanding what risks are involved in the reaction, and making sure that you are putting in cautions in place to ensure that these risks are minimized as much as possible. So one of the principles for green chemistry is maximize energy efficiency. And this can be applicable to fuel cells. So what we want to do is to be able to design fuel cells that are most energy efficient. So we want the fuel cell to be able to convert as much chemical energy into usable energy, so usable electrical energy, as possible. So what is happening here is that we have fuel cells that can be used in like an automobile, as listed here in the image. And you can see that the electricity and heat efficiency is greater than 90%, and this is compared to a thermal power generation, which is here, which is 40%, and internal combustion engine, which is 20%. So using efficient fuel cells and ensuring that we are supplying that constant reactants as fuel cells need can have the most amount of electrical and heat production as possible compared to the other two options. How do we maximize the energy efficiency in fuel cells? So there are a bunch of different factors that we can look at to ensure that we are increasing that energy efficiency as much as possible. So the first one is using a catalyst. Now we know using a catalyst is a principle of green chemistry anyway, but what does this mean in terms of fuel cells? Well, the electrodes themselves are coated with the catalyst, and this ensures that that reaction between the two reactants is sped up as much as possible. So remember that the catalyst lowers that activation energy. So this allows those reactants, as they come in contact, to be able to proceed to the products, which then increases the efficiency of the fuel cell. Electrode porosity. So we know that electrodes in fuel cells have to be porous, but when we are choosing the electrodes would depend on the fuel cell. Now, based on how porous it is, would allow the diffusion of gases in the reactants. So depending on what reactants we are using will depend on how porous the electrode needs to be. So ensuring that we are selecting that those electrodes carefully would increase that efficiency. Combine heat and power, so using heat generated byproduct, and this can be used to heat cars and buildings. So what that means is that instead of just allowing the heat that's generated to go to waste, we can use that somewhere else in the factory or in the car or in the home office or in anywhere that we're using that fuel cell. So we can use that byproduct instead of it just going to waste. Hybrid systems. So as energy is continuously produced in the fuel cell, this can be inefficient if it's not utilized. So combining different systems like a battery means that this energy can be stored. So instead of the fuel cell just continuously producing energy, which is meant to do, we can actually store that energy for later use. And this increases the efficiency and it reduces that byproduct waste. So polymer membrane electrolytes. So many fuel cells use membrane electrolytes, which are proton conductive polymers. And what this allows is that it increases that ion movement, which is what we want in the fuel cell. So ensuring that they are moving from the anode to the cathode and increasing that electricity production. Operating conditions. So like any type of reaction, reactions work better when they are under the optimal conditions they need to be under. So ensuring that the fuel cell is always operating under those conditions. We don't want it to get too hot or too cold. So how can we ensure that these fuel cells are insulated and increasing those operating conditions as much as possible? And durability, we want the materials to last. We don't want these fuel cells to break down at a quick rate. We want the materials themselves to last and last a long time. So how can we increase the durability of the fuel cells? By picking the right materials for it to run over a long period of time. So in summary, we want to make sure that we are increasing the efficiency of fuel cells to make sure that we are getting the most amount of electricity being produced and using any type of byproducts or waste that's being produced in a different process of that system. So what are the things that we can do? Well, we can use a catalyst to increase the rate of reaction, using electrolyte porosity to our advantage, combining heat and power, using hybrid systems such as a battery where possible, using polymer membrane electrolysis, increasing the operating conditions, and making sure that we are using durable products to ensure that these fuel cells last a long period of time. Any type of fuel cell production or any type of chemical reactions that's being done in industry, we want to make sure that we're adhering to green chemistry principles. And these principles focus on designing processes to minimize raw material required and waste products produced, using renewable, safe, and environmentally harmless materials where possible. We want to make sure that these are not going in the environment and affecting aquatic life or humans or any type of environmental factors as much as possible. Maximizing energy efficiency of the reactions, and this goes back to all the fuel cell stuff that we just spoke about. So all of those things, all those factors that we just spoke about increases that energy efficiency in these fuel cells. So what we're going to be looking at next is the Chapter 3 progress check. I will see you then. Bye-bye.